Welcome back to a new video. In this video we will discuss the frequency response of the MOSFET amplifier. We will discuss the source follower in this specific example. We will discuss the short circuit time constant method again to calculate our lower cutoff frequency and also our mid-band gain using the small signal model. Of course, we will see everything step by step in our calculations and verify these in SPICE simulations. Alright. Let's look at our example. We have the following given. This is the source follower circuit. You see here that the input is coupled to through the capacitor C1 into the gate, and we will measure the output through the capacitor C2 at the source. That's why it's called the source follower. We don't have the resistor here in the drain branch, which we actually usually have for our common source amplifier. We again have one DC voltage source, VDD, so the values are all shown here, so R1, R2 and the others. And we have a load here of 3 kilo ohm. The MOSFET M1 has the following specifications: threshold voltage of 2 volts. The Kn, the process parameter, is 5 milliamps per square volts. In addition, in this case, we will have a channeling modulation, which is the lambda, which is not 0 in this case. It is 0.05 volt inverse, that is 1 over volts as the units. What we want in this example, again, as we have done it for the frequency response of the other transistor amplifiers, we like to determine the maximum voltage gain, so VO over VI, and also the lower cutoff frequency, F sub L. Okay, let's discuss this in great detail. First, we start with a DC analysis. So we look at our DC circuit, and from there we need to then determine the required values to go for the AC analysis. So first we do that. Also assume that we have the saturation region operation for our MOSFET M1. That means the following. So we assume that we have to check that. What we need to check is the following two conditions. VGS must be equal to or larger than V threshold. So that is what the first condition is. And the second condition is actually saying VDS must be equal to or larger than the VGS minus the V threshold. This one is also called the overdrive voltage. Okay, now let's bring up our DC circuit. How do we do that? Well, we see that the C1 and C2 will be an open circuit for DC. So we'll lose this part of the circuit, and we also lose this part, so the RL is also gone. So we have only this mid part of the circuit actually, which is shown here. So we have the ID, which is our drain current, IS, which is our source current. These are, by the way, equal to each other since the gate current is 0. And we have the VGS here and VDS. Alright, so we need to now use this circuit to determine the required values in the DC analysis. I'll start first by determining the voltage at node G, which is a gate node. I can apply here the voltage divider rule. Why? Because the current into this branch is 0. That is allowed. If this is not 0, I cannot do that. I have to do then the Thevenin equivalent circuit method, for example. Now, Vg, which is then the voltage at node G, is then equal to R2 over R1 plus R2 times the VDD. That's shown here, and that will be then, in this case, substitute the values 7.2 volts exactly. We can now apply the Kirchhoff's voltage law, KVL, at this loop, which is this one. So I can say the following: Vg, that one, voltage is equal to the VGS plus the voltage across RS. So that's all shown here. Let me designate this equation number 1 because I need it later. The drain current for the saturation region of operation, and considering the channeling modulation in this case, is given by this expression. You see here again the Kn and VGS minus V threshold in the quantity squared. But in addition, we see here 1 plus lambda VDS. So this part is added because of this channeling modulation, and it depends on lambda but also on the value of VDS. So this is interesting, so we need to discuss this in more detail. Okay, let's call this equation number 2. And again, remember that the drain current is equal to the source current since the gate current is 0. Alright, the drain source voltage, which is actually this voltage, can be written in this format. So what I say is the following: VDS is equal to VDG, so it's actually this node voltage, minus this voltage, actually this one, so VDG. And I have also the VGS. So I actually make a circle here. So that's actually what I do. This is allowed. This is the Kirchhoff's voltage law. So I do VDS again is equal to this voltage plus that voltage. So I again come back to the same position where I started. Now why I do that, I need that actually in the later steps to substitute the unknowns. So VDG is, as said, VD minus VG. What is VD? VD is actually VDD. That's just connected right away to the power supply voltage, so the VDD. And VG is actually what we already calculated, or this voltage. So we can say VDD minus VG is 18 minus 7.2 is 10.8 volts. That is actually this voltage, so across the resistor R1. That's the exact same as this voltage VDG, which is, as said, R1 over R1 plus R2 times VDD. Again, the voltage across R1. Then again, we can say that the VDS can be then written like 10.8 plus the VGS. So you see, actually, I'm creating a formula for VDS in terms of VGS. Why? Because I will use that, I need to use that in the formula later to substitute the VDS in terms of VGS. That will make then the calculation much more easier. And I also can rewrite this in a more symbolic way, again using this formula, and then I have this one. Let's call this equation number 3. And now we can say the following: substitute this equation number 2, which is the drain current formula, into the equation number 1, which is actually this IS is equal to ID condition. So I actually do that. So you see here VG is equal to this complete expression on the right side. That is actually this one plus the RS times this complete expression for the drain current. And you see here the VDS. So that needs to be actually replaced. So I call this equation number 4. So you see actually what I should do, because I can now substitute this equation number 3, which is the VDS in terms of VGS, into the equation number 4, and then we have the following. So which is then a long expression where you see the VG again and VGS, and now you see here this lambda times this term, complete this one. Now what is then the benefit of doing this? What is the advantage of doing this? Now, well, if I look at this equation, equation number 4, I have here two unknowns. VGS is not known, but VDS is also not known. So if I can replace this VDS by something I also don't know, but the same thing, which is then VGS here, I only have one unknown, so I can solve the equation. So this is actually what I have. So this is now the expression I can use. So if you now substitute the values here, like 7.2 volts for VG, the resistor RS, the KN, and the others, then we can solve this. Now in this case, we see that we have a cubic equation. So we have a second order part here, so the quadratic and linear part. So in total we have for the VGS a cubic equation that needs to be solved. So that can be done pretty easily by a solver. And then we have 3 solutions actually. One of them is the minus 30.515 volts for the VGS, or 0.71722 volts. So mathematically we get these 3 solutions, and the third one is 2.9974 volts. Now which one is now valid? Which one we need to use? Because we have here 3 solutions mathematically, but one of them is of course the valid solution in the circuit. Well, we need to fulfill this saturation region condition, the first one. So this one is less than a threshold of 2 volts, and this one is also less than a voltage for the threshold, but this is larger than a threshold voltage. So we can say, in order to fulfill the first condition here, then this should be not valid, this is invalid, invalid, and we have the valid solution, which is the third one. This is how you actually can evaluate the valid solution from this equation. So we can say VGS is equal to 2.9974 volts. All right. Okay, let's also check the second condition in order to really sure that we are in the saturation region. Now we know that VDS is equal to VDG plus VGS. Now we know what the values are here because VGS is just calculated, and this is 10.8. We also know from this analysis here. Now taking this together will be then 13.797 volts. Well, we need to see that this here is not larger than this 13.797 volts. So VGS minus the threshold, which is then 2.9974 minus the 2, which is then 0.9974 volts, which is definitely less than this one. So the VDS is, in this case, much larger than this. So we can say our assumption is in this case valid. So saturation region for M1. All right. Let's continue now with our next step, which is now the drain current ID, because now we have the sufficient information. VGS we know, VDS we know, so we can substitute them So drain current will be then, in this case, you see that 0.005 for Kn and the VGS, and here plus 0.05 for the lambda times the VDS we just calculated. And when you now substitute this in your calculator, and you get here 8.4053 milliamps. All right, now before we jump to our AC analysis and also the small signal model for calculating the voltage gain and the lower cutoff frequency, let's discuss briefly what the small signal model parameters are. So the small signal parameters. The first one is the transconductance. So you see here the VGS in the horizontal line and the ID, which is our drain current, in the vertical axis. Now this is the plot where you recognize a threshold voltage, because from there on you get a current for the drain for our MOSFET. And you also see that this is a quadratic equation. It looks linear, by the way, of course, if you zoom in. But what we need to know here is how the relationship is between the change here in this plot at the operating point, what we call the DC operating point, because we have calculated our VGS, which was in our case 2.99 approximately. And there we have associated DC ID. Now we can say at that point, we can here draw a tangent line, and that is the slope, what we call the transconductance, and that is given by G sub M. And that can be also mathematically written like so. So this is the drain current, we know, the expression in total, and we can now calculate the GM like what you do in the other calculation for, let's say, the derivatives. So we actually calculate here the derivative, partial derivative, of course, because there are many other parameters here you can differentiate. So the partial derivative of this drain current to the VGS, and that needs to be evaluated at the capital letter VGS, which is our DC biasing setting. So at this node, or at this point, we need to evaluate our slope. Now first let's differentiate this partially, this ID, with respect to VGS, and that is then 2 times here the Kn times this one. So we drop this 2, and then you also get this, of course, this parameter here. That is the expression which you have here. Now we need to evaluate that at the capital letter VGS or DC VGS. That's shown here, so everything there will be then DC, DC, so capital letters. And this will be then actually equal to GM. But you can also write it in a different form where you directly see also this drain current. How can we do that? Now we can multiply this by the VGS minus the threshold quantity squared. Of course, then you divide it by the same thing, so you get the exact same left and right hand side. But this one here, that can be seen, this one, because of beside this 2, is actually our drain current. So we can say 2 times the drain current divided by the VGS minus the threshold is also GM. So this is a nice result, which will always be valid, also in the situation where you do not have the lambda. And you have now here the formula that can be used later for our small signal analysis to go for the voltage gain. The next one is the output impedance, which is the intrinsic impedance we have in our model for our MOSFET. Now you see here a different plot. Again, the vertical axis are drain current, but in this case we have here this changing in the VDS. So this voltage will be changed, but you will also do that for different VGS values. So for example, this is the VGS, let's say 3 volts, the other one is 4 volts, the other one is 5 volts in this case, because I have to go above the threshold, just an example. That will be, in this case, not a perfectly horizontal line, but it will be kind of a slope here, like what we have seen in the BGT. And you have actually here, if you extrapolate that back in the negative real axis, you get this voltage where you actually started, which is then minus 1 over the lambda, like the early voltage, which you see in the BGTs. And this slope here is actually conductance, so we can say 1 over this RO is our output resistance. And GM is, by the way, also here conductance, so the unit is here Siemens. So how do we calculate this slope now? Similarly, actually, what we have done for the GM. So 1 over that, which is the slope, is the partial derivative of our drain current towards this VDS, because that's where we do the operation, and we again evaluate that our bias condition, which is the gate to source DC value. So let's do that. Partial derivative of a drain towards the VDS, and that is actually shown here. So we see here this one here, there you operate actually this one as a parameter, which is then variable, and the others are constants. So 1 times this complete thing will then drop, and then lambda times this one times the kn and this complete thing squared, that will be then differentiated, and then you get actually this part. And you see here this expression where you need to substitute in here by first evaluating that at the capital letter VGS. That's shown here. So you actually just change this into the capital letter VGS. And now you substitute here this in here. So 1 over the RO is this one. So the RO will be then 1 over that. That's actually shown here. Now this is now the exact expression for the RO where you see the lambda also in the picture. But sometimes we can approximate this. This is most of the time valid. 90%, maybe 85% of the time. And it is much easier where you say 1 over the lambda and ID also. So, and you know your ID, you can also right away calculate the RO much faster, so you don't have to do this operation. All right, we have the formulas for our GM and our RO, so we can continue with our AC analysis. This is the small signal circuit for this MOSFET and this components around it. In this case, we assume that the capacitors C1 and C2 are perfectly shorted. That is what we do in the voltage gain analysis for the mid-band voltage gain. So what do we see? We see here the R2 and R1 actually in a parallel. Why? Because this one, R1, is going to VDD, which is AC ground for our small signal analysis. That's why we see here effectively parallel. We also see here the GM, VGS, which are dependent current source, so depending on this VGS voltage. And we see here this RO, which is our output resist impedance, which is our intrinsic impedance, and that is also connected to the drain node, which is also grounded, as you can see. So that's why you see here the ground. And you also see here the RS and RL effectively parallel, because the C2 is perfectly shorted here. So we have also the VO here, and also the other resistor RI. So how do we then determine here the voltage gain? Okay, let's now first designate this node G here, as said, and node D, which is our drain, and this is the source node. So this is the GM, this is the RO expression we have discussed, and these are the values for the VGS and the drain current DC. So we can first calculate the GM, because we know that is the 2 times the drain current DC over the VGS DC minus the threshold. That will result in 16.855 millisiemens. This is conductance. And RO is 1 over that, so 0.05 for our lambda, times 0.005, which is then 5 milliamps per square volts, and times the quantity here, VGS, minus the threshold, and that will result in almost 4 kilo ohms. Okay, how do we do then the voltage gain? Now we can do it in 2 steps. So this is what we need, so VO over VI, but we can separate the problem in 2 steps. We can go from the input to the gate node, so which is then VG over VI, and then we can go from this node G to the output, which is then VO over VG. That is much faster and easier to do than directly VO over VI. I will first designate this parallel combination of these 2 resistors as RG, so I will mention this as RG, and that is then in this case exactly 240 kilo ohms. So I take this part and circle this part in blue, and that is actually what you see here from the input to the node G as the voltage divider, because this part is completely open, so we can say this left side is disconnected physically in this case from the right side. So we can say RG over RG plus RI. We have here everything, so we can say this is known, so we can use that later in this expression for the voltage gain. And how about the VO and VG? Well, in this case, VO, this part encircled in red, if you can see that, this is the current which is flowing actually here in this node, and there you have 3 branches, the RS, RL, and also the RO, which is also going to ground. So effectively these 3 resistors, RO, RS, and RL, are effectively in parallel. Times, of course, this current, which is of course in the same direction, that's why we have here a plus and not a minus sign. So this is the expression for the output voltage. And for the VG, we have the VGS, like in the Kirchhoff's voltage law. So the VG is VGS plus the output voltage, because this voltage is output voltage. And we know the output voltage is shown here. And now we have the VG in terms of VGS only. Now let's take out the VGS outside the parentheses. So we have here a nice expression where you see the VGS times this complete expression in the parentheses. And now we need to do the VO or VG. Now we have an expression for VO and we have an expression of VG, both in terms of VGS, which can be then divided out. So let's see that in more detail. This is the VO and this is VG. So let's then divide out the VGS, and that is what you see here. So this is another part, the red encircled part, VO or VG. Now let's now multiply these two together in order to get the VO or VI, the complete voltage gain expression. And that's shown here. So you see here the RG over RG plus RI times the expression which you see here. So in this case it is non-inverting, but it is an attenuation. You can see that this is less than 1 and it's also less than 1. So you get actually an attenuation here. It's not a gain, but it has actually a different purpose, like for the lower output impedance and higher input impedance for voltage amplifiers. Alright, let's bring this here and then calculate now what the actual value of this AV is, which is our voltage gain, maximum voltage gain. First, the parallel combination of those three parts, RS, RL, and RO. That's actually shown here, so we can do 1 over the RS plus 1 over RL plus 1 over RO, and that to the power of -1, which is then 1 over the complete sum. That's shown here, 1 over 500 plus 1 over 3000 plus 1 over 4021, etc. to the power -1. That is then 387.3 ohms. And then we have, so we can now substitute here everything because GM is known, RG is known. That's all shown here, so you see that. And that will result in, as said, it is an attenuation, so 0.8668 as the gain, which is in this case less than 1. All right. So we have now our question A answered. So let's go now for the question B, which is our lower cutoff frequency. For that, we need to look at our small signal circuit for frequency analysis. So we'll bring up our C1 and C2 into the picture. And now we will consider here again the GM and the RO. But what we do, as we have done it also in the previous videos, we will consider the effect of one capacitor at a time, like in the superposition. So we will consider the C1 first, work out the part for that, and then we will consider the C2 also alone, and then work out the part for that. So we will look at the contribution due to C1 only and disable all the independent sources and also the other capacitors. In this case, we have only one others. So this will be shorted because that will be disabled. So disabling a voltage source will be a shorting. So this will just wire. And this is also a wire. So the C2 will be also a wire. So that's gone. So what you see is, or what we need to do is, we need to determine the impedance seen by the capacitor C1. So between the two nodes of the capacitor, we will see a impedance, and that impedance times the C1, which is our time constant. So the time constant associated with this capacitor C1 is given by this expression C1 times the impedance seen by the C1. This is, by the way, what we do the short circuit time constant method. Okay, so we need to determine the ZC1. Now, if you look at this carefully, it is actually the ZI left side in series with the parallel combination of this R1 and R2, which is the RG, what we called. So this RG, again, this was 240 kilo ohm, the parallel combination of R1 and R2. So we can say it is actually the C1 times the RI plus RG. That's actually shown here. So we do now 10 to the power -6, which is our 1 microfarad for our C1, and then times 100, which is our RI, plus 240 kilo ohm, and that will result as a time constant 240.1 milliseconds. Well, the pole frequency is the 1 over that, so that's the inverse of this time constant. So the pole frequency associated with this capacitor C1 is shown here, and that is equal to 4.165 radians per second, which is actually quite small. So this is the pole frequency for C1. Okay, we do that similarly for C2. So what do we do actually? So we go now to the contribution of C2 only and disable all the independent sources, again shorted. And also the other capacitors, in this case just C1, so that will be gone. And we look again to the situation where we need to determine the impedance seen by the capacitor C2. That means between these two nodes. Well, I see at the right side the RL, but the left side is a little bit more complicated, so that will be done now a little bit in more detail and step by step. So time constant again associated with this capacitor C2 is then given by, in general, tau C2 is C2 times the impedance because of C2. Okay, first we look at the situation. What kind of an impedance do we see if we look up? Now we see here actually at the left side nothing, so it's actually open, so we can just forget about this part. We see here GM and VGS, and we also see here RO. So this impedance is actually like 1 over GM, because that is the impedance, the inverse of the conductance, and we also see here the RO. So we can say the ZIS, which is the impedance looking in the source node, is the parallel combination of the impedance here, just the 1 over GM, and the output impedance we have determined RO. So this is actually shown here, and that will be again parallel to the RS. So let's do that step by step. So the RS, that's already there, and then parallel to that, ZIS. So first let's calculate this one. Again, as said, this is 1 over GM. That's the impedance for this part in parallel with the RO. We can do that, of course, mathematically in a different form. So 1 over GM times RO divided by the summation of these two, and then we can also multiply the numerator and denominator by GM. Then we have this expression. Now we know the RO, we also know the GM, so we can substitute here the values, and we get here 58.47 ohms. And that will be then in parallel with this RS, which is in this case 500 ohms. So that's shown here. So let's do that, and that will be then a little bit less, so then 52.35 ohms. So that will be then here. And that will be added to this 3000, which is our load resistor. So, and then the summation of that one times again this C2, it is in this case also 1 microfarad. So our time constant associated with this capacitor C2 is 3.05 to 3 milliseconds. Now the pole frequency, which is then the inverse of that one, 1 over that, that's shown here, and that is then 327.6 radians per second. Now you can already see that this is much larger than the pole frequency associated with the capacitor C1. Okay, let's summarize the result. The contribution due to C1, that's the pole frequency, which was 4.17 radians per second approximately, and that was the RG we have used for that, and this is the pole frequency because of the C2, and that is then 328 radians per second approximately. Now you can see that this is at least 80 times larger than that one, so this is way above this, so we can use here the dominant pole approximation. Again, ZIS we have used for this calculation. So in this case we have a dominant pole, and we can use that as a better approximation of the lower cutoff frequency. So we can use the following. We can say that this is dominating, so we can say the lower cutoff frequency is determined by omega C2 only, not omega C1. So this is then the 327.6 radians per second. If we now convert that to hertz, so just divide by 2 pi, that's 52.14 hertz. Okay, so we have determined also our lower cutoff frequency. Okay, let's now check our calculations using the simulation results. First, we start with DC analysis. This is the circuit where you see the drain current, the VDS, the drain to source voltage, and the VGS, gate to source voltage. And we had calculated these three, and you see actually the drain current is very close to this one, just rounding off errors maybe, or maybe the accuracy of the simulator. This is exactly as we have it. VDS and VGS is also very close to what we have here. So we can say this is perfectly fine. Okay, let's go to the Bode plot where you see both the gain and the lower cutoff frequency. You see also that this is a high pass filter characteristics, because you have a lower cutoff and then you have a flat gain for higher frequencies. And this is the circuit, of course, we have used. Now the gain we have calculated was 0.8668 in dBs. That is minus 1.242 dB, which is exactly as we see here in the simulation. So this is nice. The lower cutoff frequency we have calculated was 52.14 hertz, and this is really a nice result. You see here low cutoff frequency of 52.15 hertz. So very small difference between the calculation and the simulation here. So this is also very nice. All right, what's our example considering the frequency response of the source follower using this enhancement type MOSFET? And we have calculated the required component values, the parameters for our DC analysis, and then from there we went to the AC analysis, and we checked also our result using these simulations in the SPICE simulator. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.